Welcome to another coding tutorial, and in today's video I'm going to show you how to create this musical hexagonal Truchet tiles. I'm pretty excited about this tutorial because I've been making quite a number of Truchet tiles tutorials before, but I've been wanting to create something a little bit more complicated, and I came across this sketch by Ruben Medellin that sparked the idea for this tutorial. This video is actually part of a larger series. In this tutorial, we're going to go with the basics. We're going to learn how the hexagon shapes are built, how to create the honeycomb tiling patterns, and then we're going to end with adding some animation and then some sound. And then in the next video, we're actually going to incorporate the matter.js library to create a piece that is similar to the one that you see here by Ruben. And then in the final video, we're going to push it a little bit further. We're going to add some interactivity using the machine learning library p5.js. We're actually going to be using their body tracking model, which I've never experimented before, so that's going to be a lot of fun. Alrighty, let's look at the basics, how the hexagon shapes are built, specifically how to calculate the width, the height, and the spacing in the vertical and the horizontal directions of the tiling pattern. So a regular hexagon has 6 equal sides. If you draw lines from the center to each corner, you notice that the hexagon is actually made up of 6 little equilateral triangles, which are triangles that has equal sides. Now let's start with the radius r. This is the distance from the center of the hexagon to any of its corner. The width of the hexagon is how far it stretches from the far left corner to the far right corner, which is 2 times r. And then the height, it's a little bit trickier, so let's zoom into one of these equilateral triangle. If we slice it in half, we get a right triangle. And as you can see here, the hypotenuse has a length of r, the base is r divided by 2, and then the vertical side, which is half of the height that we're looking for. Using the Pythagorean theorem, a squared plus b squared equals to c squared, and in this case, h divided by 2 squared plus r divided by 2 squared equals to r squared. We can solve for h, and h, or height, is equals to square root of 3 times r. Now let's talk about tiling the hexagons into a grid, or the honeycomb pattern. First, let's talk about the horizontal spacing. You might think that we should move it by 2 times r, which is the length of the width, right? But if we did that, there would be a big gap between the columns. Instead, each new hexagon overlaps halfway with the previous one. So the horizontal spacing, let's call it step x, will be equals to 1.5 times r. As for the vertical spacing, there is no overlapping between the tiles, so it would just be the height, which is square root of 3 times r. But the catch is that when we build a grid, the columns are actually staggered, so every other column is actually shifted down by half of the height. Now let's move on to the 4 Truchet patterns. We're going to call them A, B, C, and D. We're going to be using the arc function to create these arc patterns, and the arc function within P5 takes in a total of 6 arguments. The first 2 are going to be the x and y coordinates of the arc's center, and then the third and the fourth are going to be the width and the height of the arc, or like of the ellipse that make up the arc, and then the 5th and the 6th are going to be the starting angle and then the ending angle of that arc in radians. Looking at the 4 patterns, you'll notice that we only really need 2 kinds of arcs, the small one and then the big one. The small arcs are simpler. They're centered right on one of the corner points of a hexagon. Their diameter is just the radius of the hexagon r, and the only thing that changes from pattern to pattern is which angles we use for the start and end. The larger arcs are a little bit less intuitive. Instead of being centered on the hexagon itself, their centers are actually at the centers of the neighboring hexagons. The one on the top, the one below, and then the one to the left. The radius of these arcs are no longer just the radius r. It actually is going to be the horizontal spacing, which is going to be 1.5 times r, as you can see from the picture here. And just like the small arcs, the start and the end angles vary based on the patterns. Alrighty, I think we're ready to start coding. We're going to start by declaring a few variables, starting with sides, which is going to be 6, right, for a hexagon, and then how about a radius of 100. And then I'm going to declare an array called corners, and this is going to be an array where we keep all the points that make up a hexagon. And then inside setup, I'm going to use a for loop that goes from I equals to 0 to I less than size, I plus plus, And what we're going to do is that we're going to figure out where the points are before we draw them out inside the draw function. So let's start by calculating the angle. So first we need to know what is the angle that divides all these points evenly, right? So it's basically 2 pi, which is 1 revolution of a circle, divided by sides, which is 6. And then this gives us the angle between each of the adjacent points. And then we want to multiply it by I so that we know exactly where each of the points are. And then we're going to use trigonometry. So x equals to r times cosine of angle. And then y equals to r times sine of angle to get the, basically convert from polar to Cartesian coordinates. And then we're going to actually add these points into the corners array. And I'm going to add it as a vector. So I'm going to add x and y points. And we can create a vector using a function, create vector. And then we're going to provide x and y. So actually, how about I print out what corners look like? So it has a total of 6 points, right? And then inside here, you can see that it has the x and y coordinates. X, y. It has z as well, but we're only going to be using x and y coordinates. All right. And then now, inside draw, what we're going to do is that we're going to use a for loop again. Now we're going to go from I equals to 0 to I less than, I mean, it's just sides, but why don't we just do corners dot length, which is also 6. And then we're going to draw them out, draw these points out. So we're going to actually use a function called vertex. And vertex takes in 2 arguments, which is the x and y coordinate. And in this case, it's going to be corners of I dot x and then corners of I dot y. And if I click run right now, you will not be able to see anything because to use the vertex function, we also need 2 additional functions, begin shape and end shape. And they do exactly what the name suggests, which is begin the shape and end the shape. So let's click run. Okay, so 2 things we need to fix. First, you can see that the origin point right now is at the top left corner of the canvas, and we calculate x and y based on this origin point. So we can do 2 things. We can actually move everything or move the origin point from here, but what I'm going to do is actually I'm going to use a translate function, and we're going to translate or move the origin point to width divided by 2 and height divided by 2. And then now everything is moved to the center here. And do you notice that this point and this point, there's no line connecting the shape? So to actually connecting the shape here, what we can do is that inside end shape here, we can provide an argument called close. And there you go. One more thing that I'm going to do is I'm going to do no fill. Alrighty. And before we move forward, I want to show you. So let me declare n equals to 0. And then we're going to draw an ellipse at position corners of n dot x, corners of n dot y, and then let's do a size of 10. I just want to show you where the points are. So 0 start at this location here, and then it moves clockwise, and so on. So 0, 1, 2, 3, 4, and 5. Okay, next we're going to actually create another array. Let's call this one midpoints, and we're going to keep the midpoints in here. So the midpoints are going to be the points between the 2 corners. Inside here, what we're going to do is that we're going to use another for loop that goes from I equals 0 to I less than corners dot length I plus plus, and then we're going to set 2 variables. How about C1 and C2 for corner 1 and corner 2, and this will be corners of I, yeah, and then C2 will be corners of I plus 1. And we can't just do I plus 1 like this because it will give us an error once it is out of bound. So let's say that I is already equals to 5, I plus 1 will be 6, which is too much. So what we can do is that we want it to loop around, right? When it becomes 6, I want it to be 0. So 0.5 and 0.5 and 0.0 we'll be finding the midpoint between those. And how to do that is that we can use an expression called modulo, which is this percentage sign here, and then 6, or actually let's do sides. And basically this expression returns the remainder between the division of two numbers. In this case, I plus 1 and sides. So let's say that this number is 1 mod 6, there's no remainder. So as in the remainder is 1, so nothing happens. But once it is greater than 5, let's say this is 6, right, which is out of bound already. So 6 mod 6 will give us 0. So that's how we're gonna loop things around. All right, so once we have this, we need to find a midpoint. So let's do mid. We're gonna create a vector, and this vector is, let me just write it out first, p5.vector.lerp. So we're going to use this method lerp to find the point between the 2 points. And it takes in 3 arguments. So it needs the first vector, the second vector, and then the third one is the amount, which ranges between 0 and 1, which is where it is between those 2 vectors that we want. And we want it halfway, right? Because it's the midpoint. And then what we can do is we can just add this point mid inside our midpoints array. Okay, so let's just draw it out just to see that we have it correct. So for let I equals to 0, I less than midpoints dot length I plus plus, and then we're gonna do ellipse. And then how about midpoints of I dot x, midpoints of I dot y, and 10. All right. And if I put this as 0, just to show you where is the first midpoint, can you guess? It is this one. Yeah, because C1 and C2, the first one is this point and this point, right? So 0, 1, 2, 3, 4, and 5. Perfect. Now that we have the hexagon, next we're going to create the 4 Truchet patterns. What I'm going to do now actually is, how about we create a function first. Let's call this draw hexagon, and then I'm going to put these inside here. Okay. All right, and then I'm going to create another function called draw pattern. And this draw pattern is going to take an argument. Let's call it type. And these are the types A, B, C, and D that we talked about earlier. I'm going to be using the switch statement to create different conditions to pick the type that we're going to use as the tiling pattern. To do that, the syntax is switch and then type. And we're going to be providing different cases. So let's say case A, and then once it matches with that, then it will basically just run anything that is inside here. And we're going to do this for A, B, C, and D. B, C, and D. Okay. All right, so with the case A, as you can see from this picture here, we're going to have a line that goes across the midpoint, this one and this one, right? So let's start with that. So actually, I'm going to also just call it draw pattern now, so we can keep checking. And we're going to do case A. All right, so If I click run, nothing happens yet. Now we're gonna be using the line function, right? And it's going to be what? Midpoints of 0, 1, 1 dot x, and then midpoints of 1 dot y, right? And then the other point is 2, 3, and 4. So 4 and 4. All right. Okay, so the second part is we're going to be drawing an arc here and an arc here. So we're going to use the arc function. And the center of this first arc is going to be this point here, which is corners of index 0, right? So it's going to be corners of 0 dot x, corners of 0 dot y. And then the next part that we need is the diameter, the width and the height. And as we talked about before, it is actually just the radius. And then lastly, it's going to be the starting angle and then the ending angle. So I'm actually going to declare small arc length here because they're all going to be the same at 2 pi divided by 3. So it's going to be, yeah, a third of the whole circle, right? All right, so the start of this arc here, so we know that here is 0. So the start is actually also 2 pi divided by 3. So 2 pi divided by 3. And then the ending will be 2 pi. So it's just the start, right? Plus small arc length. Run. Yay. Perfect. Okay, now let's just copy and paste this for the next one, which is this part here. The corners here is 0, 1, 2, and 3. So 3 and 3. Radius is the same, as in diameter is the same. And here, we're going to start from this point here, which is negative pi over 3, right? So we just do negative pi over 3 and add it by small arc length. And now we're done with pattern A. Okay, so let's go to pattern B, which is still quite similar to this one. So we actually can copy this one, right? Which is this. All right, and then now we're going to draw this one and then this one. So I'm going to copy and paste this one more time. So this is corner 0, 1, 2. Okay, and the starting and the ending angle. So this is what? It's pi plus pi over 3. Yeah, what is that? Pi is 3 pi over 3, 4 pi over 3. Let's try it. 4 pi over 3. 4 pi over 3 plus small arc length. Yay, okay. Last one is at corners of 4. And this one is, yeah, this one is easy. It's start from 0. So 0. And then it just goes to small arc. Nice. Right, we're done with A and B. Let's go to C. So for C, we'll start simple with the line in the middle, right? So I can just copy and paste this. Okay, the challenge is now drawing this piece here and then this piece here. So as I showed you before in the picture earlier, it's going to be the big arc length, right? So let's do big arc length, and that is actually going to be pi over 3. Because if you can see, if you can imagine it coming down like this, right? And pi is just this line across, which is half the circle. It is a third of that pi. All right, so the center point now is going to be, we're gonna do this one first. So this point here will be 0 for x, and then y will be h, height. And then the diameter will be, so the radius is 1.5, right? Or the step x size, right? But because the third and the fourth arguments here are actually the diameter, so it's 1.5 times 2. So it's going to be 3 times r. And then for this one, we're going to need from here to here. So start here, it's going to be pi plus pi over 3 again. So 4 pi over 3, 4 pi over 3 plus big arc length. Oh, we never actually calculate what height is. So let's do width and height. So height is what? Square root of 3 times r, right? And then width is 2 times r. We can do the step x and y after. So I think this should work. Yay! Okay, and then the last one, I'm just gonna copy and paste this. So instead of 0, h, it's gonna be 0, negative h, right? The center is at the top here. Same diameter, but the start and the end is gonna be what? Pi over 3, right? From this point. All right, so that's pattern C. And then the last pattern, pattern D. Pattern D is going to have the midpoint. No, it doesn't. It has this small arc on the right side, right? Right. Okay, and then it's going to have this big arc here and this big arc here. So let's do this bottom left one first. So it's going to be an arc. The center for x, it's actually going to be negative step x, basically. So 1.5 times r, and then height, because we need to move it down. So the center of this left neighboring one, which is going to be height divided by 2, and then radius will be the same at 3 times r for the big arc, right? And I mean the diameter, and then the start and the ending angle. So 0, and then yeah, it's going to be negative pi over 3, and then end at negative pi over 3 plus big arc length. It actually is just 0, but let's keep it consistent. Nice. And then last but not least, this one here, still at the same width location, right? Which is here, but instead of h divided by 2 for the y, it will be negative, and it will start at 0, then end at big arc length. Nice. Okay, so before we put everything inside a class, what I want to do is that I want to show you how to rotate it. So I'm going to actually create a function called mousePressed, and basically what I want to do is I want to rotate it. So inside this, below this translate function, we're going to call rotate, and we're going to rotate it by angle. And then we're going to set angle originally at 0, and every time we press the mouse, we're going to add angle by pi over 3. So that's how much we want to rotate the shapes. And yeah, okay, let's try. Rotate, 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 rotate. So that's this pattern. Let's just try for, where is it? Type, okay, A, B, and C. And you already saw D. Okay, let's put it inside a class. So now let's come to this arrow here, click create file. I'm gonna call it hex.js, and then we're gonna go to index.html first to add in this JavaScript file, change the name here to hex.js, and that's how we incorporate a new JavaScript file into the program. Right, so let's go back to Hex here. We're going to start by writing class, call it Hex, and then we're going to start with the constructor function. So what do we need inside here? So we're going to keep width and height here as global variables, also sides and radius. We're going to take all of this, but actually I can just copy these parts. Okay. All right. So we need to add what? This dot corners, and then this dot midpoints, right? And then don't forget to put all the this dot global. These are all global variables except for these and these and these and these, I think. Okay, and then next I want to create a few more variables here. So let's do position, set it as a vector, and we're gonna give the parameter x and y. Then the third one is actually type. We also want to know the type, and yeah, I think we can just start from there. Then we're gonna call a function, create a function, a method called display, and display is basically us doing this. Then we'll copy the draw pattern and draw a hexagon next. Okay, so instead of translating everything to width divided by 2 and height divided by 2, we want to translate it to the new x and y position, right? Angle, we also want angle. Let's put it down here, this dot angle, set it to 0. And then we need this dot for these two functions too. We can delete this for now. This will be the type, right? It will be this type here. Okay, let's go back and copy the two functions here. We don't need mousePressed right now. Okay, let's see, display. Okay, so inside here, we don't need the word function, right? So because we set switch case to this dot type already, we don't need to provide additional arguments into these methods here.
A few moments later.
All right, now that we put all the this dot, let's just try to create one hexagon. So let's come here, let hexagon, and then hexagon will be a new hex object, right? Let's put it at the same location here. So width divided by 2 and height divided by 2, and then let's do type, how about A? Then we just do hexagon dot display. Okay, A, B, C, and D. Perfect. Now comes the tiling. So we're going to create a bunch of hexagons. So let's change this to and array. And then how about we calculate step X and step Y now. So we already know step X will be 1.5 times R, and then step Y will be height, right? What we need to calculate next is actually columns and rows. So let's do columns, rows, and then columns will basically be width divided by step X, right? But because this division could be a decimal, could return a decimal point, we're going to put in floor as well. And same for rows, height. divided by step y. And then inside here, we're gonna write a nested for loop that goes from I equals to 0 to I less than calls, I plus plus, and then j equals to 0 to j less than rows, and then j plus plus. And then inside here, first we're going to make the hexagon array into a 2D array, and then inside here we're going to do hexagons of I and j, and it will be a new hexagon object, right? But not at width divided by 2 and height divided by 2. It's going to be at what? So x will be equals to I times step x, and then y will be equals to j times step y, right? And we're going to copy and paste these nested for loop so that we can call display. Okay, so a few things that we need to fix. So the first one, as you can see here, it's not even a tile. If you have seen this multiple times, or me doing this, it's because the display function here, we use the transformation functions, translate and rotate. What we need to put in also is push and pop. Push saves the transformation, and then pop returns it back before calling the next transformation. So we're not accumulating the transformation, basically moving the origin point from the origin point of the previous tile. So this should fix the first problem. Okay, let's make it a little bit smaller. Let's do, how about 50? Okay, so as you can see, it's not the pattern that we want, basically. So I'm actually going to put E here so that we don't see the inside, so it's easier. So the thing that we need to fix is actually the step Y, right? As we initially looked at this, every other column needs to be shifted down by height divided by 2 so that they kind of lock themselves into this honeycomb pattern. So what we're going to do is that we're going to say if I mod 2 equals to 0. So this basically returns either 0 or 1. And if it's 0, so it's an even row, we're going to say that y will be equals to this. Otherwise, else y will be equals to this plus h divided by 2. And that fixed it. Now you can see that we're missing a little bit on the sides here. So what we want is, because floor, it rounds down the number. So if we add 1, fix the issue. But also, let's say that we make this a bit smaller. You can see that it doesn't fix the issue completely, and that is because we're missing the next hexagon on the right and bottom, because when we divide by step x, we're missing that like tiny additional side of a hexagon. So what we can do is that we can add width by r, and then we add height by h divided by 2. And this should fix this issue. Okay, and I guess you can also just add 2. You can just kind of play around with this just to make sure that the tiling pattern fits within your screen. Okay, so once we have this, let's bring back, how about we start by actually create an array called types, and we're going to put A, B, C, and D in here. And we're going to do let type be a random value within the types array. We're going to put type in here. Ta-da! Nice, huh? Okay, great. So basically now we have the Truchet patterns, hexagon Truchet patterns. Now what we want to do next is that we want to be able to animate it. So I'm going to go back to hex.js file here and start by animating this angle. So why don't we add speed? Let's set it to 0.01. And then we're gonna create a method called update. And basically update can just be this dot angle plus equals to this dot speed. So we basically just increment the angle, right? Okay, let's call the update method. Then now all of the hexagons are moving at a constant speed, which is pretty great. I don't want them to move at the same time. I've done quite a number of these type of interaction, or not like the animation. So in my previous Truchet pattern tutorials, I did it based on how we hover the mouse on the pattern, but then this time we'll just do it randomly. So I'm going to call this start rotation. So this is the method that basically will tell us to start. So instead of have it hover, right? I said like this could be a condition. There could be a condition where, you know, when you hover the mouse, then you start the rotation. But I'm going to use this underneath a condition based on a random number. So to start this rotation, we're going to create a few more variables. This one is a Boolean variable. So let's call is rotating. We're going to start it as false. So when we want to start the rotation, we're going to use a conditional statement that says if not is rotating, no, this dot is rotating. So if it's not rotating, then what we want is, actually we're going to change this angle here to be current angle. And then we want a few more. So we want this dot start angle, this dot end angle, which is the target angle, and then we also want this dot progress. So progress will basically tell us if it reaches the end angle yet. And last but not least, we also want the base angle. And the base angle basically is once we rotate, we want to keep it at that location and we want to move it from there so that it doesn't snap back to the original or like the beginning or when angle equals to 0. First, if it's not rotating yet, we're gonna say this dot is rotating equals to true. And then we're gonna set the current angle to be the base angle. And then the end angle basically is going to be the base angle plus pi over 3. That's how much we want it to rotate. And then inside update here, we basically also just want to move the current angle by this dot speed, right? But also inside this, we also want to also check if this dot is rotating is true, then we do this. We only want to increment it. And then we want to write another conditional statement that says if this dot current angle is greater or equals to this dot end angle. So this is when it hits where it's supposed to be, right? Then first we're gonna reset this dot is rotating to false. And then we want to set this dot current angle to be equal to this dot end angle. We don't want it to move further. And then we also going to set the base angle to the end angle too. So this is where it's going to start in the next movement. And then else here, we're going to, so if it's not rotating, then this dot current angle should just be the same as the base angle. And inside here, we're now rotating by the current angle. Okay, I think so. Let's see. So if we run we already call update here. Nothing happens because we need the start rotation, because right now is rotating is false for all. So what I want to do is that I want to call a conditional statement, an if statement that says if random, which returns a value between 0 and 1, not including 1, is less than let's do 0.05. Then we're gonna randomize the column and row. So let's do column, let's call it C, gonna be an integer. So floor between 0 and columns, floor between random of columns. So if you provide just one argument inside random, the minimum will be 0. And then R will be floor of random of rows. And then we're going to do hexagons of C and R dot start rotation. Okay, let's try this. Oh, they're moving. Nice. Okay, so next, it's hard to see, so let's add some colors and things like that. So I'm going to start by, I have a color palette that I want to use, and then I want to change the background color to be this blue color. Okay, so let's go to hex here. We're gonna create some color variables here. So let's do active color will be a random color within the palette that we just put in, P-A-L-E-T-T-E. And then let's call hex color. So this would be the color for the hexagons. So I'm going to do, let's do the color white, but make it not super transparent. And then what else do we need? Yeah, I'm gonna call it default color, and this is the color of the pattern. So I'm going to set it to almost white. Actually, yeah, okay. Maybe we don't need this hex color. All right, so for display, I want to start by putting stroke weight for everything to be larger at 5. Okay, and then we're going to set the stroke color here. And how I'm going to put in as an argument here, this is an if statement, but new syntax. So if this dot is rotating is true, then we're gonna change the color to this dot active color, and if not, it is going to be this dot default color. So this is basically saying that use active color if this returns true, and use default color if this returns false. New syntax. Let's try it. Okay. And actually, I want the stroke color for the hexagon to be stroke slightly bluer than the background. Yeah, what do you think? I honestly like it more. I'll show you the actual hexagons here. I actually like it more without the hexagons. So I'm going to actually comment it out. Ooh. We need no fill for the patterns as well. No fill. Okay. All right, on to the last part. Let's add some sounds. So we're actually going to be using the new version of the P5 library. So we're going to actually switch this to the version 0.5. Ta-da! And we're going to be using the sound library. So I'm going to click on here. And the reason that we clicked on here is because normally by default, the package for the sound library is not being added. But now that I click that part, this sound library is being added, which we need to do this. All right, so first what we're going to do is we're going to click this plus sign, and then I'm going to create a folder actually. Let's call it assets. And then now inside here, we're going to upload the sound file. So you just drag and drop your sound files, or you can use mine. All right, so once they are uploaded, what we need to do, so with the 2.5 model, we're not using preload anymore. We're going to be using the async and await syntax. So super simple. First, what we're going to do, let's just load one sound file. Let's do this first one. So I'm going to call this sound. And then inside, before the setup function here, we're going to call async, right? And then let's do it here. We're going to set sound equals to, normally how we load this, we just do sound equals to load sound and then the name of the sound, the file here, right? Which is going to be assets /ring1.wave. But with the async, we need a wait here. And then let's try this. Let's click run. No error. But now we need to play the sound. So very simple. We want to play the sound when one of these hexagon starts to rotate. So I'm going to put it inside here. So let's do sound.play. All right. Okay, but that's only one sound. I want to add all of the 5 sounds that I have. So what I'm going to do actually is I'm going to create an array called assets, and I'm going to put in the names of all of these. So ring 1, right? So it's just ring 1 to ring 5, 2, 3, 4, and 5, and then just change these 3, 4, and 5. And then sounds will also be an array. And then here we're going to use a for loop that goes through my assets array. And then we're going to do sounds of I equals to await load sound. And then instead of doing the name here, what we're going to do is we're going to do assets plus, it will be just these strings, right? So assets of I. And then here, instead of doing sound.play, we're going to randomize. So let's do s equals to random of, how about sounds, and then we'll just do s.play. Moment of truth.
A few moments later.
Oh, I forgot. I missed this backslash. Let's try it again. Nice. Okay, let's make it a bit faster. We need all the ringing sound we can get. All right, so that ends the first part of this 3-part series. So I hope that you enjoyed this one. It's a nice one to learn about a new, more complex Truchet tiles, and then, you know, you have some music, some sound added into it too. So that's super fun. In the next one, we're going to be adding some physics into the sketch using matter.js. So stay tuned to that one, and I hope that you give this one a try.